another problem statement, and today's problem statement is the largest binary search tree. So before you go to the problem statement, I would like you guys to go like, share, and subscribe, and share this channel with your friends and people who actually need it, people who want to improve their DSA game at the end moment of their placement season. This is really a game changer. You should see all the POTD playlist, and the playlist is going to help you in a certain manner. Okay, so before doing anything else, so if you haven't seen my GFG Geek for Geeks POTD binary search tree playlist, go and just click over there, and you will get to see all the videos related to binary search tree, and it's a very helpful resource. So what is today's problem statement? Today's problem statement is the largest binary search tree. So the largest binary search tree, what it is saying is that we will be given a binary tree, okay, binary tree, and we will have to find the largest size of the binary tree, which is a binary tree itself. So it's a binary tree with itself a binary search tree, okay, and here the size equals to the number of nodes in the subtree, okay. So if, say for example, if I see a tree as 1, 4, 6, 8, and 4, if I see what is the subtree of this particular tree, it's 4. 4 is 1. Okay, so there is no subtree with size greater than 1 which forms the output is 1. Okay, why is the output is 1? Because we are going to find the size of his largest subtree, which is itself a binary subtree. So there is no subtree which is greater size than 1 which follows a binary subtree. All the leaf nodes are equal size equals to the 1. So if you see the leaf nodes, these are the leaves. These are the leaves. They have size equals to 1. So obviously the answer is 1. Let us take an example. This will help you understand more better. So if you have a binary tree 6, 6, 2, 2, 1, 3. So if I want to check what is the biggest subtree available, the biggest subtree available, which is itself a binary subtree, is this one. Which is 2, 1, and 3. Okay. So in this particular case, I can figure it out that we have to return the size of this tree. So the size of the tree is the depth of the tree, or the depth of that depth means the height of the binary search tree. The height of the binary search tree. That's the reason we have a time complexity as O of n. We have a time complexity as O of n. Okay. So 2, 1, 3 with the size 3 is the largest binary subtree with 3. Okay. So how we are going to do is, so we have quickly made a class info, and we have made in the info we have taken the constructors. We have taken a minimum value and a maximum value. This is the minimum value. Okay, I've taken a minimum value and maximum value, and this is the size. This is my size. Now we are taking the largest binary search tree. This is the function. Okay, this is the largest binary subtree. We are taking a node, and after returning, we are making a solve function. Solve is taking the root, and then we are giving the height of that. The reason we are using size. Size means we are taking the height of the tree. Okay. So let us come to the our solve method. So we are taking, if the root is equals to run, then we are going to return new. In the info we are passing the maximum value and the minimum value and 0. So max value and minimum value is the lowest amount of value you can store, and maximum value is the highest amount of value ranging to infinity you can store. So in the info left equals to solve dot left, so we are going to recursively call this function for left parameter and right parameter. Okay, so we are going to solve this by root dot left and root dot right, initially for the left pointer and the right pointer. Okay, now we are checking if the left dot max value, the maximum value present, left dot max value is lesser than root dot data, the data present at that particular position, and the data is also lesser than the right dot min value. Okay, so then we are going to return minimum of the data and the left value, and maximum of we are going to return in this order. So in the information, what are the information we're going to pass? The minimum value, maximum value, and the size. So the minimum value is the minimum value between the data, and the left value. Okay, and maximum value, this is minimum, and for maximum what we are going to do is we are going to do the data. Okay, and we are going to take the right max value, and we are going to also do the left plus right of size plus 1. Okay, so initially what we can do is we can run this particular check that okay, I am at my particular data, so my data and the value at my leftmost minimum value. So this is the leftmost minimum value, this is the rightmost maximum value, and what else we have. So we are taking the mat of minimum of leftmost and rightmost, and for maximum we are going to take first the right value and then left plus right plus the total size of the left and right. So say for example I have 3, 4, 5, 6. Okay, now I have 5, now I have 8, 9, okay, and I have 10. So if I see the subtree, the depth of this particular subtree, the depth of this height of the subtree is 1, 2, 3. Okay, the height of the subtree is, let me just check what they have given the size, right? So size, height of the subtree, okay. Here size equals to the number of nodes in the subtree, number of nodes in the subtree. So if you see the number of nodes in the subtree, there are 2 nodes, okay, and number of nodes in the subtree is 1, 2, 3, okay. There are 3 nodes. So similarly, this will be the largest subtree, okay. And whenever we are doing like this, how we are comparing and how we are checking, we have to understand, okay. So we have to understand by this that if the left value is lesser than root dot data, okay. So if you know there are some conditions of a binary search tree, binary search tree rules, okay. I will just tell you the rules of the binary search tree, okay. Just gonna quickly tell you the rules of the binary search tree. This will be easy. So binary search tree rules. The value of the left node must be smaller than the parent node, and the value of the right node must be greater than the parent node. Okay, so I don't know whether this is a binary subtree or not, but you can pretty much see the example of this particular question. So the value of the left must be lesser than the parent, and value of the right must be greater than the parent. Okay, that's what it said. Okay, the rule is applied recursively to the left and right subtree. Now we're going to check. Yes, we are first checking the left is lesser than the parent and the parent is lesser than the right. So we have, this part is clear, this part is analyzed, this part is understood. Now we will say, bro, we have understood this part. Now how we are going to calculate the information of the depth of the maximum value. That's the reason we are taking the minimum of this value. We are taking the minimum of the parent. This is the parent and the leftmost minimum value. And similarly, we are doing it for the rightmost value, okay, parent and right value, as well as the size of the left plus right size plus 1, okay. So this is how we can get the information, and the information we are going to solve the largest root of the binary search, and we are going to return the integer.min value. So integer.min value is the negative highest value, integer.maximum positive value, and after that we have math.max of left size and right size. So this is our main calculation. We are taking the left and right size, and then we are going to return which is the highest, which is the most depth point we have reached in our finding the most valid highest binary search tree. So that's all about the largest size of the binary subtree, and I hope you could understand the problem statement, and we are looking forward to solve more problems. Thank you.